In this video, we're going to be looking at what's called curvilinear motion. So the context is we can imagine that we have an object that's moving through the XY plane, and we're going to be talking about things like calculating the object's velocity or calculating its acceleration. So let's take a look at how the information in this section might be presented. So we'll be given a formula for the horizontal position of our object, so we'll call that x, and that will depend on time. So that's just saying that's our x position at any given time, and then separately we'll be given a formula for the y position. So both of those positions will be given in meters, and we'll say that time, little t, is measured in seconds. So once we've got x and y given to us, we can make a table of values to figure out the object's position at any given point in time. So let me just add a little bit of detail to the bottom of this table, just so we can see how we would calculate a typical position. So let's say we want to know where the object is at 5 seconds. So we'd say, okay, t equal 5, we'd plug that into our formula for x. So we'd have 1 minus 25 would be negative 24. That's our x position at time equal 5. And then at t equal 5, plug into the y. So we'd have 4 times 25, which is 100. In a similar way, you could get a position at time 0, time 1, time 2, etc. Now, if we wanted to actually make a plot of the path that the object is traveling, it would only be the x and y coordinates that we would care about. So we would just disregard the time column at this point. We'd look at our x and y coordinates, and then we can start to plot these points. So at time 0, we can see from the first row here that our object is at the point 1, 0. So let's say that's here. The scale we're going to use, let's say our horizontal axis goes in increments of 5. So this would be -5, that would be -15, and then let's say our vertical axis goes up in increments of 20. That's just so we can fit all the points nicely on here. At time 1, we're at the point 0.4, so that would be about there. At time 2, we're at -316, so about there. And in a similar way, we could plot our other points. If you like, you could even label, this is our position at time 0, this is our position at time equal 2 seconds, etc. So you can get a sense of how that object is traveling. So now let's jump into a definition. We're going to talk about velocity. So we're going to say that velocity in the x direction will be written v sub x. So I'm just using a script v with a little subscript x there. So that's our horizontal velocity. And then we've got a formula for how to calculate that. So the way we actually calculate that, dx by dt. And in a similar way, if you wanted velocity in the y direction, or vertical velocity, we could say, the notation we'll use is v sub y. The way we'll actually calculate it, dy by dt. Now, when we say velocity, velocity represents speed and direction. So if someone asks you to find the object's velocity at a certain point in time, we're really looking to give two quantities in our answer, both speed and direction. So let's see a couple formulas for how to calculate speed and direction if we know the horizontal and vertical velocities. So I'm actually going to erase this picture here. We'll redraw it after we've written down the formulas. So here are the two formulas that are going to be really helpful for us, the formulas for calculating speed and direction. So let's say that we already know our v sub x and our v sub y. The way we're going to get speed, well, we'll call that just v. So overall speed is v, and we're going to say that's the square root of vx squared plus vy squared. So let's start to understand where this formula comes from. If we draw a picture, imagine our object is moving, let's say, this way. So it's got some horizontal velocity and it's got some vertical velocity. So the horizontal velocity v sub x, vertical velocity v sub y, and what we're trying to find is the overall speed. So we can just think of that as being the length of the hypotenuse. This is a right angle triangle because our horizontal and vertical directions are perpendicular. And so with that diagram drawn, we can say, oh yeah, that's just going to be the Pythagorean theorem. So v is going to be the square root of v sub x squared plus v sub y squared. Now, if we want to talk about the direction in which our object is heading, the way we do that is we just talk about what angle is that velocity going in, or what angle is that making to the positive x-axis. So the way we can do that is by using the arctan function, because we can say this angle theta is going to be arctan of v sub y over v sub x. So that's almost right. The problem is this formula, properly speaking, works when you have a right triangle, but we may well be in one of the other quadrants. So the proper thing to say here is that we may need to add 180 degrees to correct the quadrant. And we'll see all the details about that when we jump into the example in a minute. So the proper formula for theta is it's arctan of v sub y over v sub x, possibly plus 180 degrees. So let's jump into a fresh page and we'll go through all the details of calculating speed and direction. So here's our problem. It's the same motion that we described in our initial example here. Horizontal position, x equal 1 minus t squared. Vertical position, y equal 4t squared. What we want to do is find the velocity at t equal 3 seconds. And that means find both speed and direction. So first thing we'll do is we'll find our horizontal velocity. So v sub x, the way you do that is you take the derivative of x with respect to t. So I think I won't write that down, and we'll instead just write down what the actual derivative is. So take the derivative of this guy with respect to t, you get minus 2t. Now we're interested in what's happening at t equal 3 seconds. So let's sub in, and we can say, well, specifically at that time, our horizontal velocity, -6 meters per second. Okay, and let's do the same thing for the vertical velocity. So v sub y is the derivative of y with respect to t. So let's look back up here at y. There we go. Take the derivative. You'd have 8t. And then in this line here, what we're doing is we're subbing in t equal 3. So at the time that we're interested in, our vertical velocity is 24 meters per second. Great. So then, if it's helpful for you, you can draw this little right triangle over on the side just to help remember your formula. So you've got your horizontal and vertical velocities. If you want your speed, and symbols, we're going to call that v. Let's just think about the Pythagorean theorem. We need to do the square root of v sub x squared plus v sub y squared. So that's the square root of, well, the square of -6 is 36, plus whatever 24 squared is. We'll put that into our calculator and we'll just round off. So that's about 24.7, and nice to give units in our answer. So that's meters per second. Okay, so next thing we need is the direction. So when we talk direction, we're talking about this angle theta here. Okay, so let's think back to pre-calculus. Remember that tan theta is opposite over adjacent, right? So for this particular triangle, you could say the opposite side is v sub y and the adjacent side is v sub x. So from there, we can say theta equals arctan of v sub y over v sub x. So you're just basically applying arctan to both sides when you do that. But the catch is, you may remember this from pre-calculus, arctan can only return values in this quadrant or this quadrant. When you put arctan of anything into your calculator, it's returning to an angle, and that angle can only ever be between -90 and +90 degrees. It's just a restriction on the arctan function. So if our angle ends up being somewhere over here on the left, what we actually need to do is add 180 degrees to get the correct answer. So the way I usually phrase that is put this into your calculator, go arctan of v sub y over v sub x, and then you may need to add 180 degrees. So I usually just put that part in brackets. Okay, and the way you figure out if you need to add 180 degrees or not is you actually need to just make a little sketch of the specific vector that you're working with. So that's sort of a preamble to jumping into the question. So with that sort of discussion out of the way, let's just go over here and let's say direction is theta equal arctan v sub y over v sub x, and then possibly plus 180 degrees. And very first thing we're going to do is we're going to sketch our actual vector to decide if we need to do that correction or not. Okay, so here's how that sketching process works. Let's look back to the top and figure out what our specific velocities were. Okay, so at t equal 3, we said we're just looking at this line here. At t equal 3, our horizontal velocity was -6, and our vertical velocity was 24. So that tells us that our object is actually moving this way. And that tells us that when we calculate our angle, we're going to get an angle, just roughly something like maybe 135 degrees or maybe 120 degrees. It's going to be some angle in this second quadrant here, and we know that from drawing a picture. So yes, we do need to add 180 degrees. Anytime your angle is in quadrant 2 or quadrant 3, you need to do this plus 180 degrees thing. Okay, so let's do the calculation. We are going to go arctan of taking our vertical velocity, which is 24, dividing by our horizontal velocity, -6, close the brackets. Just make sure your calculator's in degree mode for when it's going to spit out this angle, and then go plus 180 degrees. And you should see an angle of about 104 degrees for your answer. Okay, so final answer to the problem then, you could say the velocity is 24.7 meters per second, and then just say at 104 degrees. Okay, and then let's just write a reminder about theta based on our discussion. Let's say add 180 degrees when your angle is in either quadrant 2 or quadrant 3. And when we say quadrant 2 or quadrant 3, we mean either this quadrant here, this quadrant there. So some people will think of that as just saying when your angle points left. So when your angle is either pointing left and up or left and down, that's when the correction happens. Whereas when your angle is pointing right, arctan is going to give you the correct angle, and there's no adding 180 degrees required. So this is the same curve that we had actually plotted earlier. I put a little bit of scale on here that you can see. We've got 5 units along the x-axis, 20 units along the y-axis. And right at the opening of this video, we plotted this trajectory, this set of positions that looked something like that. Okay, so that's our position curve. And let's say this dot right here, you can see that represents the position at time 3 seconds. So what we just did was we calculated the velocity of our object at t equal 3 seconds. We said the horizontal velocity was -6, the vertical velocity was 24, and so we're creating this little triangle here. And you could say the hypotenuse of that triangle, if you think of it as a vector, that's our velocity vector. So just let's zoom in on that. Draw a bigger version of that. Okay, so position curve, which may or may not be a straight line. This is the point t equal 3, so that's our position at t equal 3. We draw our horizontal and vertical velocities at that time, and then zooming in on this hypotenuse, we can think of that as a velocity vector. So the velocity vector at t equal 3 seconds. So what we're trying to get at from this picture is the fact that the velocity vector is tangent to the position curve. Rather than saying velocity, it might be better to say velocity vector. Sort of implied because velocity is a vector, but we're just trying to highlight the geometry here, that the velocity vector is tangent to the position curve. So the velocity vector touches the position curve just right at that position there. And the velocity vector describes the direction in which the position curve is moving. So our position is x equal 3t squared, y equal 1 minus t squared. We're going to find the velocity at t equal 4 seconds. So let's start with horizontal velocity. V sub x is 6t, and we can plug in what's happening at our specific t value. So at t equal 4, v sub x is going to be 24. Let's do a similar thing for vertical velocity. So v sub y is going to be negative 2t. At t equal 4, v sub y is going to be negative 8. So if you like, you can just put a box around that because those are going to be the numbers that will be important in our calculation. So from there, we'll find speed, which we'll call v. If you like, you can draw a picture of this triangle where you've got your horizontal velocity, vertical velocity, you've got your speed on the hypotenuse, it's a right triangle, and your angle theta that we'll talk about in a minute is going to be sitting right there. So it's your angle to the positive x-axis as usual. So to get speed v, we'll think Pythagorean theorem. It's going to be the square root of v sub x squared plus v sub y squared. So plugging in some numbers, square root of whatever 24 squared is plus the square of negative 8 is 64. So putting all that into your calculator, that's going to come out to about 25.3 meters per second. Great, and then let's talk angle. So from our previous angle discussion, we know that it's important to draw a sketch, even just a very rough sketch of our velocity vector, just so that we know what quadrant we're in. So let's look back up here to our horizontal and vertical velocity. We know horizontal velocity is 24, and we know that vertical velocity is negative 8. Okay, so basically what that tells us is we are in quadrant 4, and that means there's no correction required. So you only have to add 180 degrees if your angle points left. So if you're in quadrant 2 or quadrant 3, you have to do the correction. But if you're in quadrant 1 or quadrant 4, no correction required. Okay, so we can say theta is arctan of v sub y over v sub x. In general, we would say plus possibly 180 degrees. We've decided that nope, we don't need to do that here. So our angle is going to be arctan of negative 8 divided by 24, no correction required. So putting that into our calculator, we get about negative 18.4 degrees, and that seems reasonable according to our sketch. So you could just leave your answer like that, or you could say something in words to summarize it. You could say your velocity equals 25.3 meters per second at negative 18.4 degrees. So now that we've talked about velocity, we're going to talk about acceleration. So let's just do a definition here. So we'll define acceleration in the x direction. If we want symbols for that, we'll write a sub x. And the way we'll actually calculate that is we'll just take the derivative of our horizontal velocity. So if you just say this to yourself in words, to get horizontal acceleration, just take the derivative of horizontal velocity. To get acceleration in the y direction, or vertical acceleration, you could say, the symbol that we'll use is a sub y, and the way we actually get that, take the derivative of v sub y. So again, in words, vertical acceleration is the derivative of vertical velocity. So we're just extending the idea that acceleration is the derivative of velocity. And when we talk about acceleration, remember that it's going to have a magnitude and direction. So meaning we're going to say a certain number of meters per second squared, and we're going to say a specific direction like 20 degrees. So let's talk formulas. I think I will erase this triangle. I'll redraw it over on the side. And let's think about our two key formulas that we're going to need here. So I'll put stars beside both of these. So we're really going to be drawing a very similar triangle as to what we drew when we were talking about velocity. So imagine that you know your horizontal acceleration, so we'll call that a sub x, and imagine you know your vertical acceleration, we'll call that a sub y. So we get this nice right triangle. And when we talk about, well, what is the overall acceleration, we're really asking what is the length of the hypotenuse. So we just call this the magnitude of the acceleration. In symbols, we'll call that a. So think of that as the overall acceleration if you wish. And that's just going to come from the Pythagorean theorem. So we're going to say a is the square root of a sub x squared plus a sub y squared. And then the other thing we need is our angle theta. So we'll say, very similar to what we said with our velocity discussion, we'll say to get this angle theta, just take arctan of the vertical component divided by the horizontal component. So that gives you your angle theta. But we may need to add 180 degrees to this. So it's the same discussion as before. You need to add 180 degrees when the angle points left. So if the angle is in quadrant 2 or quadrant 3, arctan will give you the wrong angle and you need to add 180 degrees to correct for that. Great, so with that, let's try an example. So here are our positions, x equal 5 plus t squared, y equal 1 plus t cubed. We want to find the acceleration at t equal 3 seconds. So let's start with the horizontal direction. We'll first find horizontal velocity and then we'll find horizontal acceleration. Okay, so horizontal velocity is what you get if you just take the derivative of x with respect to t, so that would be 2t. And if you take the derivative again, then you're getting horizontal acceleration. So it goes position, turns into velocity, turns into acceleration as you take the derivative. Okay, let's do the same thing for the vertical direction. So we would first get v sub y, and then we would get a sub y. So vertical velocity, if we take the derivative of this, 3t squared, take the derivative again, and you get vertical acceleration. So that's 6t. Okay, then we can plug in whatever t value we're interested in. In this case, it's t equal 3. So at that moment in time, the horizontal acceleration is 2. Notice that the horizontal acceleration is constant in this problem. So no matter what time value you're at, the horizontal acceleration is always going to be 2 meters per second squared. But the vertical acceleration does depend on time. So the vertical acceleration at t equal 3 seconds is 18 meters per second squared. Great, so once we've got those two numbers, if we like, we can highlight them because we're going to use them twice in what's coming up here. We can draw our special triangle if we like. So let's say we know our a sub x and our a sub y. We're going to figure out a and we're going to figure out theta. Okay, so let's find a. According to the Pythagorean theorem, we're going to go square root of a sub x squared plus a sub y squared. So that's the square root of 4 plus whatever the square of 18 is. And that comes out to 18.1 meters per second squared. So always good to put units on there. If we're talking acceleration, it's meters per second squared. So that's what's called the magnitude of the acceleration. So that's half our answer. And the other half of the answer is to find the direction. Okay, so let's think about our formula. We're going to say theta is arctan of, well, our y component, a sub y, divided by our x component, a sub x, and then possibly plus 180 degrees. So I just write that as bracket plus 180 degrees question mark. Okay, so the way that we decide if we need to add or not is we just make a little sketch of our specific acceleration. So let's come back to here where we've got our numbers. At the point in time that we're interested in, horizontal acceleration is 2, vertical acceleration is 18. So that tells us that our angle is pointing right. So there's no correction required. Only if the angle were pointing left in quadrant 2 or quadrant 3 would we need that correction. So that's good. So our answer then is going to be arctan of, we're going to take 18 divided by 2, no correction required, and that comes out to about 83.7 degrees. So that seems reasonable according to the sketch that we've got over on the side. Just from eyeballing that, yeah, that looks like about 84 degrees. So here's our answer. You can say the acceleration at that point in time that we're interested in, 18.1 meters per second squared, and then you can just say at 83.7 degrees. So we've got one more problem to go in this section, and before we do that problem, we need to have a little recap of the chain rule. So we're going to do a couple of quick examples here before we get into our last problem. Let's say someone gives us a formula for y in terms of x. Okay, so this would correspond to someone actually giving us the curve that a particular object is moving along. So this curve is some sort of parabola. Just imagine someone gives you this parabola and they say, hey, your object's moving along this curve. So x depends on time, because as time ticks along, the object is moving, so we can predict what the x position is going to be, and then once we've got the x position, we can figure out y. So let's say that we want to find dy by dt. Okay, well, this is where the chain rule is going to come in. Y is not a function of t. So we'd say, well, to get dy by dt, what we could do, what we know how to do, is take dy by dx. So we know how to take the derivative of y with respect to x because we've got this formula highlighted here. But then in order to make this equation true, we would need to multiply by dx by dt. So just in a symbolic way, you can imagine the dx's canceling from the top and the bottom. And so we can convince ourselves that this equation really is true. We really do have dy by dt on both sides of the equation. But the reason why we rewrite it like this is because dy by dx is something that we know how to calculate. And dx by dt would be something that's presumably easy to calculate, or maybe even given in the problem. So this equation really comes down to the chain rule. So it's the chain rule, but it's not the intuitive version of the chain rule. It's that second version of the chain rule that we said we were going to see later on in the course. So this is the time where we're now seeing it. So what's going on here is you can think of y as being your outside function, and you can think of x as being the inside function. So we're saying take the derivative of the outside function while keeping the inside function the same. So we're just taking the derivative of the outside function with respect to the inside function, and then take the derivative of the inside function. So it really is the same chain rule as we saw before, but it's just a different presentation. And so usually the best way to think about it is just the fact that these dx's will cancel. And so you convince yourself from an algebra point of view that that should be valid. Okay, so how would that help us in this specific problem? Well, let's say someone has given us a formula for y in terms of x, and they're asking us to find dy by dt. Well, we would say dy by dt it's going to be the derivative of y with respect to x. So -2 plus 16x, and then that all gets multiplied by dx by dt. So let's just break into a new page and just sort of try a fresh version of that. Always good to just put some new numbers in there. So let's say someone gives you y equals, say, 3x minus 19x squared. And let's say the problem is to find dy by dt. So we would look at this and we would say, oh, well, y appears to be a function of x. So the fact that the question is asking for dy by dt tells us that there's a chain rule involved. So we would say to get dy by dt, well, let's think what we could do. We could go dy by dx, but then in order to make this equation true, we'd have to multiply by dx by dt. So you can just symbolically imagine those dx's canceling out, and that would convince you that that formula is correct. So the value of doing that is that it gets you a little bit further towards computing what dy by dt actually is. So this dx by dt, we don't know. We would just have to leave it as is. But the dy by dx, that's just our normal derivative, the 3 minus 38x. So that's exactly the sort of idea that we're going to use in our last big problem for this video. So in this problem, we are given a position curve, y equals 100 minus 0.02x squared. And we're also told something about the horizontal velocity. So horizontal velocity is constant throughout the problem. it is 9 meters per second at every point in time. Based on that, we want to find the object's overall velocity at t equal 3 seconds. So that means finding both the speed and the direction. So the way we would start here, the way we would normally start these velocity problems is we would think about v sub x, and then we would think about v sub y. So v sub x, we were told in the problem, is constant, so it's going to be 9 no matter what time value we're looking at. So v sub y then becomes the interesting one. Okay, so let's write v sub y question mark, and most of our early work in the problem is just going to come down to finding this v sub y. So let's think about what v sub y is. It is the derivative of the y position with respect to time. So dy by dt is just another way of saying v sub y. Remember, y is position, so if you take the derivative of vertical position with respect to time, you're going to get vertical velocity. And this is where a chain rule comes into play, because we could say, well, see, we can't directly take the derivative of y with respect to t, right? Because y is in terms of x in the formula that we've been given. So what we can do is we can take the derivative of y with respect to x, but at this point the equation is not quite true, right? So we need to multiply by something to make it true. So we can multiply by dx by dt. And just to convince yourself that this formula is valid, you can just kind of mentally imagine canceling out the dx's there. So we can say, yeah, what we've written down is valid. Okay, so this, what we've just written down here, that's called the chain rule. It's the second version of the chain rule, not the intuitive version, but you could say it's the algebra version of the chain rule. And the reason why this helps us is because these two things are velocities. So dy by dt, that's the rate of change of y with respect to time. So that's what we would call vertical velocity. And this thing here, the dx by dt, that's the rate of change of our x position with respect to time. So that's horizontal velocity. It's just a different notation for it. But this is saying to get your vertical velocity, just take dy by dx, which you can calculate, and multiply by the horizontal velocity. Okay, so let's do that. So we'll say v sub y is going to be, let's look back up at y. So here it is at the top of the screen. And we're just going to take the derivative with respect to x. So that would give us minus 0.04x. And then that has to get multiplied by vx. Okay, and that's helpful because remember we were told in the question that v sub x is equal to 9. So right away we know that's 9. Okay, so progress, so much progress has been made. So v sub y is equal to negative 0.04x times 9. Okay, now we want to sub in t equal 3, right? So we want to get a specific value at t equal 3. What we need to figure out is what our position is at t equal 3. So if we can figure out our x position at t equal 3, then we can sub that in, and then we'll have our vertical velocity from there. Okay, so let's think about x position. To get your x position at any point in time, you would take your initial position, and then you would add on your vertical velocity times time. So let's just think about from a physics point of view whether this is valid. So to get your horizontal position at any point in time, think about where you started and then take your speed and multiply by time. So this would be like taking a certain number of meters per second, multiplying by a certain number of seconds. Yeah, for sure that would give you a certain number of meters, and that would tell you how far you had traveled from your initial position. Okay, so the catch in these type of problems, we're going to assume that our initial position is 0 unless we're told otherwise. But if it said something like the object is starting at, 2 meters right of the origin or something like that, then you would say, okay, our initial position is 2. So our initial position is 0. Remember, horizontal velocity here is constant throughout the problem. So it's 9 meters per second. How many seconds have we traveled for? 3. So what is our x position after 3 seconds? 27. Okay, so I'm going to put this stuff in a box because it was really an intermediate calculation in terms of now getting our vertical velocity. So with that, we're ready to figure out v sub y. Okay, so I'm just going to come back to the equation that we had right up at the top here. So at time equal 3 seconds, what is v sub y going to look like? Well, it's going to be negative 0.04 times this x value that we just figured out, 27, and then times 9. So we can put that all into the calculator to get negative 9.72. So now at this point, we know our horizontal velocity. It's 9 meters per second throughout the problem, and we've just now figured out our vertical velocity to be negative 9.72. So from here, we'll be able to finish the problem and just get our speed and direction quickly. But I just want to run through the logical steps that we had to do to find v sub y, just in case you're doing a problem like this again in the future. So first step I would say to finding v sub y is thinking about this chain rule. So let's think of that as one step. If you say this in words, your vertical velocity is going to be dy by dx times your horizontal velocity. So think of that as one step. Then what happens is you've got this mystery x in here that you still need to deal with. So you could think of that as then being a second step. So how are we going to get x? Well, just think initial position plus speed times time. That way you can get your x value. And then take that x value, whatever x value you figured out, and just plug it into what you had up here. So we did that there. So really 3 little steps to getting our vertical velocity in this type of problem. So if we're now happy with that, then we can just finish up with doing our speed and our direction as usual, then we'll be done. So if you like, you can draw your special triangle here. So you're going to have your horizontal and your vertical, and you're going to have your overall speed, and you're going to have your angle giving your direction here. So to get your speed, we'll call that v. We're going to take the square root of each of our velocities squared and just summed up. So square root of 9 squared plus negative 9.72 all squared. Put that into our calculator, and that comes out to about 13.2. Remember, it's always important to think about what quadrant you're in, because we may need to correct when we actually calculate our arctan function. So let's look here at our horizontal and vertical velocities. V sub x was positive, and v sub y was negative. So our angle is doing something like that. Because that point's right, no correction required. So we can say theta is arctan of, we're going to go v sub y divided by v sub x. And that gives us an angle of about negative 47.2 degrees. So just remember to always do this sketch to figure out if you need to add 180 degrees or not. So here's our answer. Velocity at that point in time, 13.2 at negative 47.2 degrees. And really the hard part of the problem here was finding that v sub y, because we had to use the chain rule. So that is all about curvilinear motion. Thanks for watching.